If gravity is pulling down on this particular flower vase with G force, then we can actually see that there is actually a component which is acting directly opposite. This is a line of force that is acting in that particular direction, and this is one more line of force acting in another particular direction. When an object is moving under the influence of gravity alone, it is known as free fall. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. Today we are going to look at an important topic which we did not actually cover in the previous classes, that is regarding equilibrium and free fall. So what exactly is equilibrium and what exactly is free fall is going to be discussed in this particular session. So let's dive right into it. So what exactly is equilibrium? We know that equilibrium just means that it is a balance of something. So what exactly is balanced here? Since we are talking about forces acting on objects, we are naturally talking about the balance of forces. Imagine that you have a table. Imagine that you have a particular table like this. Imagine that you have a table like this and there is a beautiful flower pot that is just sitting on top of that particular table. So you go out wherever you want to go. Maybe you go for a run, maybe you go for a swim, maybe you go to meet your friends. So anyways, when you leave this house, you can see the flower pot sitting on that particular table. And after a long time, you come back and you can still see that particular flower pot sitting in that very exact spot. It is not moved, it is not tilted over, it is not falling over, it is just simply sitting just like that throughout the day in that very particular same position. So why is that happening? The very simple reason is that, sir, no one is touching it, no one is moving it, so obviously it will be there only. So my question is the same, that is, if no external forces like no one is touching it, no one is pushing it, if no external factors like that is affecting this particular flower vase, then does that mean that no force is necessarily affected by this flower pot? No, right? There is obviously the force of gravity pulling on it downwards. There is a slight wind resistance. There is static frictional force acting on it. So different forces are obviously acting on it. There is obviously the atmospheric pressure also putting force on this particular flower vase. But it's not moving, it's not flying away, it is not sinking into the ground. So why does this happen? So the simple reason why this does not happen is because even though there are several forces acting in different directions, there are equal amount of forces which balance out the imbalances in these forces. That is, if gravity is pulling down on this particular flower vase with G force, then we can actually see that there is actually a component which is acting directly opposite. That is, the normal reaction force is actually acting on that particular plane also, which cancels out the effect of gravitational pull. That is why the flower pot is not sinking down. Just like that, because of the atmospheric pressure, the pressure also exerts a force. So that is also cancelled out because of various forces acting in the opposite direction. So you have to understand that an object in physics is said to be in equilibrium only if all the forces acting on it cancels each other out. That is, the net force acting on this particular object should be equal to 0. It does not matter that many forces are acting on it from different directions. It is okay. Many forces individually can act on this particular object and they can have different values. Maybe this can have 50 newtons, maybe this can have 10 newtons. So different values can also be exerted upon this particular object. But the only point is that for this particular object to be in a state of equilibrium, that is, to be in a balanced state, all these forces should be cancelled out. That is, they should have their opposite elements acting on it so that the net force, that is, here it will be, let's say, here minus 50 is acting, here minus 10 is acting, so that the net effect of this particular force applied on that particular object or felt by that particular object should be equal to 0. Then if the net force experienced on this particular object is 0, then we can say this particular object is in a state of equilibrium. Now, that brings us to one more point. Should an object be in absolute rest? Oh, we cannot say absolute rest, but anyways, should this object be in a state of rest for it to be in a state of equilibrium? Absolutely not. You can be in a state of rest or uniform motion and still be having perfect equilibrium. For example, the moon is in a perfect state of equilibrium. Does an object have to be at rest for it to experience equilibrium? Not exactly, because any object that is uniformly moving or any object that is in rest also can experience equilibrium. The only condition is that if all the forces acting on it cancels each other out, that is, the net force experienced by any particular object, when it is 0, then we can say that particular object is in equilibrium. Whether is it in rest or is it in motion does not bother us, because the only criteria we are looking for is that the net force acting on that particular object should be equal to 0. So again, I told you about what is equilibrium. One more thing we have to learn is about concurrent forces. So what exactly is this concurrent forces? To understand that, we need to understand what exactly lines of forces are. So we actually know that Newton actually saw the world in terms of forces, and he used lines of actions to represent those forces. All this was actually discussed previously. So again, so imagine that all these are lines of forces. This is a line of force that is acting in that particular direction, and this is one more line of force acting in another particular direction, and you have one more force which is acting in the upward direction. So you have actually 3 lines of forces acting. So one is going in the upward direction, one is going in this particular direction, and one is going in this particular direction. So the common thing about all these lines of forces is that they pass through a common point in space and time. That is, they all seems to be having a common point of intersection. So if any of the forces that you are experiencing or that you are witnessing is seeming to have a common point of intersection, then we can say that those kind of forces are actually known as concurrent forces. So concurrent forces is simply those forces whose lines of action intersect at a common point. That is, if 3 forces are acting, let's say this is F1 and this is F2 and this is F3. All of these forces have a common intersection point here. Let's call it as A. So all of these forces actually have a common intersection point at A. Hence, they are known as concurrent forces. So if concurrent forces are acting on a body, we can say that for that body to have equilibrium, the vector sum of all these forces should be equal to 0. Then only that body will be in equilibrium. That is one more scientific way of saying it. If concurrent forces are acting on any object, the vector sum of that object should be equal to 0 for that body to be in equilibrium. That is, concurrent forces are simply forces whose lines of action meet at a common point. So in order to understand this even more simply, we can use a practical example. Imagine that I have a board here. Okay, I have a plain board here through which I have tied a string. So I have tied a string like this. This is my string which I have tied like this. Now I'm going to hang a weight on top of this particular string. So what happens? Obviously, because of the weight, the string will start to stretch. So what will happen? The string will stretch like this so that the weight hanging is pulling it down. Let's say this is a weight of 5 kilograms. So 5 kilogram weight is acting on it. Hence, it is pulling this particular string down like this. So why do I need to say this? That is because here also different forces are acting on this particular point. That is, if I am saying that, okay, there is a force acting in this particular direction, that is the force of gravity. That is, this mass is being pulled down with the force of gravity, that is G, 9.8 meter per second square. And there is also multiple other forces acting on this particular board. One force is tensional force. So there is a tensional force in this particular direction and in this particular direction. There is tensional forces T1 and T2 acting here. So again, what is the point of saying all this? So what I want you to understand here is that there is 3 forces, 3 vectorial components acting on this particular plane, which means that there are 3 vectors acting like this, all having, let's say this is vector 1 going in this direction, vector 2 going in this direction, vector 3 going in this direction, or simply forces F1, F2 and F3 acting in 3 different directions. But all of them seems to be having a common point of intersection. All of them seems to be having a common point of intersection. So we can say that different forces having different lines of action, all are meeting at a common point. Hence, they are known as concurrent forces. And is this falling down? Is this swinging away? No, right. They are stably kept together, which means there is equilibrium towards this particular setup, which is another way of saying that all of these forces vectorially cancel each other out. The net force experienced for this particular system is actually 0. Hence, we can actually say that this system is in equilibrium. That is the most simplest way to explain equilibrium of a system using vectorial forces. That is, even though there are different forces acting in different directions, since they are concurrent forces, that is, they all seem to be having a common point of intersection, and these forces vectorially cancel each other out. Hence, the system is in equilibrium. Or we actually can do this particular thing in the lab setup. We can actually find what is the magnitude force that is being applied on this particular board, that is this particular point. We can actually do that, and we can actually find it using parallelogram law of vector addition. If we take these 2 sides as the sides of a parallelogram, then you can find the resultant using parallelogram law of vector addition. That we will actually do it in the lab, but for now just understand that what is concurrent force and what is equilibrium. The next topic is already been discussed. It's very simple, that is the concept of free fall. So we do know that any object, let's say this is Earth, and there is a big coconut tree here, big coconut tree like this here. So when the coconut falls, it falls really fast down. If anyone is standing under that, they'll get severely injured or they'll lose their consciousness. So why does this coconut fall? Or why does the apple fall? Same reason, gravity, right? So because of gravity, the earth is pulling down on this particular coconut, which means that the particular object that is having a mass is falling down onto earth. So this effect, that is, when an object is falling down, or simply when an object is moving under the influence of gravity alone, is known as free fall. For example, if you throw a rock directly upwards, after some time, that particular object that is having a mass m, rock of mass m, seems to be moving downwards, accelerating. And this acceleration is provided by gravity. So free fall is nothing but any object that is moving under the influence of gravity alone. That is why it is known as free fall. So gravity will be pulling down on this particular object, and at every second it will accelerate until it reaches a point where the air resistance comes into play, and there will be something known as terminal velocity. But we are taking the ideal condition where there is no air resistance, nothing blocking that. So this particular object which is moving under the influence of gravity alone is known as free fall. Any object that is falling under the influence of gravity is known as free fall. So that is free fall, and I like to discuss one more interesting example of free fall. That is, In free fall, that is, if a mass is falling under the influence of gravity, we won't be able to feel our weight. That is, imagine that there is a big building and you're going upwards in a lift. So here you are, this is you, and you're going upwards in a lift. Suddenly what happens is that the lift cable broke down. The lift's cable, which was pulling you upwards, suddenly broke down, which means that now you're actually falling down at a speed retake. Now you're actually going to fall down to your doom. Or simply, you're falling down under the influence of gravity. It is very scary. It is very sad. Yeah. But as physicists, only thing we are concerned is a mass m is falling down under the influence of gravity, which means that now when this particular object is moving down, you are not experiencing weight. So what is the difference between weight and mass? So we do know that mass is just the amount of substance contained in any material, or anything that occupies space is known as mass. That is the loose definition that we can give here right now. Actually, mass is a characteristic property because of the interaction of the Higgs field and everything. But let's say mass is simply the amount of substance contained in any material. And what is weight? When there is a mass m and gravity is pulling down on it with gravitational constant g, then a total force will be experienced. This total force experience, that is m times g, is known as your weight. That is why if you weigh like 50 kilograms near the equator, and if you go to the polar region, you'll be weighing about 50.5 or something. That is because there is a slight change in gravity. And that is exactly the reason why gold and certain other materials are measured through their masses. That is, there is an equipment which measures their masses. You might have seen where there are equipments which measure masses. It is known as a weighing balance, where there is a setup like this. In one hand, they will put gold or whatever you want. Let's say this is gold. They'll put gold inside that. And we know that this gold will experience the mass being pulled down with gravitational constant g. So it will experience a weight, a force which is acting downwards. And in the other pot, we will keep adding weights similarly, so that we will add the exact amount of weight, so that we like add the exact amount of objects, masses being 1 kilogram, 2 kilogram, or 0.5 grams, 0.2 grams. We'll keep adding those weights in until these two balance. That is, both of them, if the gold plate is like this, we'll keep adding on weights onto the other one, so that both of them will balance out. Which means that now same amount of force is also felt in the very next basket, which means that the net effect of the forces is cancelled out, which means that now we are actually measuring what is the mass in these baskets. We are not measuring what is the weight. If we want to measure weight, we only need one. But we are cancelling out the effect of gravity, and hence we are measuring what is the mass contained in that particular object. That is how you actually measure gold. That is how in olden times you actually buy fish. Okay, this much fish, this much price. You might have seen that in movies and all that, or even in courthouses, there is an equipment called the weighing balance, where there are two baskets like this. So this is called a weighing balance. It cancels out the effect of weight, and you can directly measure what is the actual mass present in any object. So that is the difference between mass and weight. Anyways, so when this particular case happens, that is when you're going up really fast and suddenly the cable breaks and you're in free fall, that is you're falling under the influence of gravity, you will actually experience something known as weightlessness. That is something known as weightlessness. That means that the effect of gravity pulling down on your mass is not being felt. You actually experience weight and we can actually measure weight because when there is a floor and you're standing on it, you're actually exerting a force, or earth is pulling down on you with a force G mg, so that earth is pulling down on you with a force of mg, and you are exerting an equal amount of force in the opposite direction called the reaction force n. So this particular reaction force is what is being measured, and that is what is given as your weight. But when you are in free fall, there is no floor to step and exert weight on, because you and the floor are both falling at the exact same rate, which means that you can't really apply a force within this particular system, which means that you won't be experiencing weight. You don't have to study all this. The only thing you have to understand is that any object that is falling under the influence of gravity alone is known as free fall. And what is weight and what is mass? Weight is when gravity pulls on a mass, that is, the total force experienced by that particular mass is known as weight, and the mass is just the amount of substance contained in that particular material. That is it. This is just an interesting effect. In earlier times you used to have this, but now it's removed. But anyways, this is the same reason, gravity is the same reason why astronauts don't feel weight. That is, astronauts can float around in the International Space Station also because they are constantly falling. That is, they are constantly falling under the influence of gravity, and they are just rotating around. So you can check upon this and you can learn an interesting concept. Really interesting phenomena and theories came out of this particular concept, that is free fall. Einstein imagined many things. He even said that if I am falling down onto the ground, then the ground must be accelerating up towards me also. There are different concepts and different theories regarding free fall, and interesting results coming out of free fall, and how gravity is affecting different things. It's a whole new thing. If you have time, you can look upon it, and there are interesting theories regarding this. For now, just understand what is equilibrium, what is concurrent forces, what is mass, what is weight. That is the only thing you have to understand from this particular topic, and from that we are finishing this particular chapter. And I hope you have understood all about what is concurrent forces, what is equilibrium, what is free fall, what is weight, and what is mass. The only thing you have to remember about concurrent forces is that they have to have a common point of intersection. And again, for equilibrium, the only thing you have to remember is that for an object to be in equilibrium, it is not necessary that that object has to be in a state of rest. It can also be moving. There also, if the forces cancel each other out, and then we can also say that that particular object is in equilibrium. So that is all for today. I'll see you in the next class. Thank you.